Hello friends, today let us see how we can use Polymath to solve ordinary differential equations. We have already seen how Polymath can solve linear equation, can solve non-linear equation. Uh, Today we'll see how to solve ordinary differential equation, and for that what we need to do is we need to click on either this icon and we directly get this window, or we may go for a blank file and we can select out of this and differential equation open and we get this. So this is the window for solving ordinary differential equation. Now ordinary differential equation we come across in chemical engineering for so many things. We get ordinary differential equation when we solve any model which is at unsteady state, where we get d by dt with respect to time. We have ordinary differential equation solution in terms of vapor liquid equilibrium when we are trying to perform residue curve mapping. And commonly we encounter it while we write material balance equation, component wise material balance equation in chemical reaction engineering when the reactions are going on. Since that being one of the most classical example, let us take down two examples wherein we are having first a single reaction going from A to B, and in second case there is a series of reaction A to B, B to C. Now let's try to simulate the first reaction with A to B, and the expression for dCA by dt would be minus K1 into Ca with initial concentration of A being 10 is done. So we have defined the equation. Now our job is to define the values of K1. So K1, let's say it is 1. We press OK, and we have to also give the time frame for the simulation to take place. We set time t equal to 0 to time t equal to 5 and press OK, and we know that now this is ready for simulation. Before we simulate it, let us put a tick on graph so that we get the graphical result. If you are interested in values of concentration with respect to time at every time interval, we may also press we may also take this. Right now we'll just simulate it and we see that this is what we get. And as we can see that the concentration of A is falling with time, but it eventually reaches to somewhere in between 0 and 1. So what we can do now is we can increase the time from 5 to 10 maybe, and then simulate it. This will give us an idea that, see, the final value is 0.000454, and you can just see that the concentration is almost 0 after your time unit 7. Now if we change the K, let's say K 1.5, and simulate it, you can just see that the concentration falls down to 0 in between 3 and 4. So there are two time units different is there. So if K value increases, naturally the concentration falls to 0 much faster compared to your earlier answers. So now if you simulate that, it's this. Now suppose if we make it to 2.5, and we can see that further the things have changed, and it is almost 1 to 2 minutes. So yeah, K can be like this. Now if we look at reaction in series, where A gives B gives C, and we have got K1 for A to B and K2 for B to C. If I want to write equations pertaining to this, I say dCA by dt equals minus K1 into Ca with initial concentration as 10 mole per liter, and we also add for Cb, which is K1 into Ca minus K2 into Cb with initial concentration of B being 0, and we also have dCc dt. This is equal to K2 into Cb with initial concentration of Cc as 0. So these are our differential equations, and when we write explicit equation for K1 and K2, let's initially keep both of them 1 1, and we integrate it from 0 to 10, and we plot this, and we see that what we get is this, with highest concentration of B being somewhere in the range of 3.8, which we can confirm in terms of the tabular results. So 3.67 is the highest CV, and CC is almost 10, and your CA almost 0. Now if we change K1 from 1 to 1.5 and we simulate this, you can see that my CV value has increased to 4.43, which is also visible here. Earlier it was between 3 to 4, now it is beyond 4. If I make it this as 1.5 and K2 as 0.5, and I am increasing the difference between the two, I can see that this is 5.7. and another thing which is happening now is that the concentration of CC is a little bit decreased. Now if I make this as 2.5 and this being 0.1, you can see drastic change in our results, and those results are, you just see that this is 6.1 and my maximum value of B is 8. See this, and that means if I want to get B highest, I should run the reaction between 1 and 2 minutes where I get maximum value, and that is in between 8 and 9, and this you can see that is almost kind of restricted below 6. This was a bit exaggerated. However, if I got somewhere like this, you can just see that still my B concentration is rising almost to 7, and that too within 1 minute. So this is where I should stop my reaction. So my CC is produced in least amount. Other way around, if my K1 is less and K2 is high, naturally what I'll have is my B value would be very less and C will be high. So this is your B in between 1 and 2. So this you can analyze with the help of Polymath. Any ordinary differential equation, any number, you can see that there are 3. Any number you can solve, and as I told you, it is just by adding differential equation, auxiliary equation, initial and final value, you can get this. So solving ordinary differential equation using Polymath is pretty simple. You just add the equations properly and press this simulate tab, and you get all the results. You can analyze them by changing different values of your parameters or maybe time intervals, which will help you to understand the physics of the system in better way. Thank you.